In the branch of mathematics known as real analysis, the Riemann integral, created by Bernhard Riemann, was the first rigorous definition of the integral of a function on an interval. For many functions and practical applications, the Riemann integral can be evaluated by the fundamental theorem of calculus or approximated by numerical integration. The Riemann integral is unsuitable for many theoretical purposes. Some of the technical deficiencies in Riemann integration can be remedied with the Riemann-Stieltjes integral, and most disappear with the Lebesgue integral. Overview: let f be a non-negative real-valued function on the interval a, b, and let be the region of the plane under the graph of the function f and above the interval a, b. We are interested in measuring the area of S. Once we have measured it, we will denote the area by. The basic idea of the Riemann integral is to use very simple approximations for the area of S. By taking better and better approximations, we can say that, in the limit, we get exactly the area of S under the curve. Note that where f can be both positive and negative, the definition of S is modified so that the integral corresponds to the signed area under the graph of f. That is, the area above the x-axis minus the area below the x-axis. Definition: partitions of an interval A. Partition of an interval a, b, is a finite sequence of numbers of the form each, xi plus 1, is called a subinterval of the partition. The mesh or norm of a partition is defined to be the length of the longest subinterval, that is, a tagged partition of an interval a, b, is a partition together with a finite sequence of numbers subject to the conditions that for each I. In other words, it is a partition together with a distinguished point of every subinterval. The mesh of a tagged partition is the same as that of an ordinary partition. Suppose that two partitions and are both partitions of the interval a, b. We say that is a refinement of if for each integer I, with, there exists an integer such that and such that for some j with. Said more simply, a refinement of a tagged partition breaks up some of the subintervals and adds tags to the partition where necessary. Thus it refines the accuracy of the partition. We can define a partial order on the set of all tagged partitions by saying that one tagged partition is greater or equal to another if the former is a refinement of the latter. Riemann sums choose a real-valued function f which is defined on the interval a, b. The Riemann sum of f with respect to the tagged partition x0, xn together with t0, Tennessee -1 is. Each term in the sum is a product of the value of the function at a given point, and the length of an interval. Consequently, each term represents the area of a rectangle with height f and width xi plus 1 minus xi. The Riemann sum is the area of all the rectangles. Riemann integral. Loosely speaking, the Riemann integral is the limit of the Riemann sums of a function as the partitions get finer. If the limit exists, then the function is said to be integrable. The Riemann sum can be made as close as desired to the Riemann integral by making the partition fine enough. One important requirement is that the mesh of the partitions must become smaller and smaller, so that in the limit, it is 0. If this were not so, then we would not be getting a good approximation to the function on certain subintervals. In fact, this is enough to define an integral. To be specific, we say that the Riemann integral of f equals S if the following condition holds. For all epsilon greater than 0, there exists delta such that for any tagged partition and whose mesh is less than delta, we have unfortunately. This definition is very difficult to use. It would help to develop an equivalent definition of the Riemann integral which is easier to work with. We develop this definition now, with a proof of equivalence following. A new definition says that the Riemann integral of f equals S if the following condition holds. For all epsilon greater than 0, there exists a tagged partition and such that for any tagged partition and which is a refinement of an. We have both of these mean that eventually, the Riemann sum of f with respect to any partition gets trapped close to S. Since this is true no matter how close we demand the sums be trapped, we say that the Riemann sums converge to S. These definitions are actually a special case of a more general concept, a net. As we stated earlier, these two definitions are equivalent. In other words, S works in the first definition if and only if S works in the second definition. To show that the first definition implies the second, start with an epsilon, and choose a delta that satisfies the condition. Choose any tagged partition whose mesh is less than delta. Its Riemann sum is within epsilon of S, and any refinement of this partition will also have mesh less than delta. So the Riemann sum of the refinement will also be within epsilon of S. To show that the second definition implies the first, it is easiest to use the Dabo integral. First one shows that the second definition is equivalent to the definition of the Dabo integral. For this, see the article on Dabo integration. Now we will show that a Dabo integrable function satisfies the first definition. Fix epsilon, and choose a partition such that the lower and upper Dabo sums with respect to this partition are within of the value S of the Dabo integral. Let if R equals 0, then f is the zero function, which is clearly both Dabo and Riemann integrable with integral 0. Therefore, we will assume that r greater than 0. If m greater than 1, then we choose delta such that if m equals 1, then we choose delta to be less than 1. Choose a tagged partition and with mesh smaller than delta. We must show that the Riemann sum is within epsilon of S. To see this, choose an interval. If this interval is contained within sum, then where mj and mj are respectively the infimum and the supremum of f on. If all intervals had this property, then this would conclude the proof. Because each term in the Riemann sum would be bounded by a corresponding term in the Dabo sums, and we chose the Dabo sums to be near S. This is the case when m equals 1, so the proof is finished in that case. Therefore, we may assume that m greater than 1. In this case, it is possible that one of the is not contained in any. Instead, it may stretch across two of the intervals determined by. In symbols, it may happen that this can happen at most m-1 times. To handle this case, we will estimate the difference between the Riemann sum and the Dabo sum by subdividing the partition at. The term in the Riemann sum splits into two terms. Suppose, without loss of generality, that, then so this term is bounded by the corresponding term in the Dabo sum for yj. To bound the other term, notice that it follows that, for some, since this happens at most m-1 times, the distance between the Riemann sum and a Dabo sum is at most. Therefore, the distance between the Riemann sum and S is at most epsilon. Examples. Let be the function which takes the value 1 at every point. Any Riemann sum of f on 0, 1 will have the value 1. Therefore the Riemann integral of f on 0, 1 is 1. Let be the indicator function of the rational numbers in 0, 1, that is, IQ takes the value 1 on rational numbers and 0 on irrational numbers. This function does not have a Riemann integral. To prove this, we will show how to construct tagged partitions whose Riemann sums get arbitrarily close to both 0 and 1. To start, let n be a tagged partition. Choose epsilon greater than 0. The t have already been chosen, and we can't change the value of f at those points. But if we cut the partition into tiny pieces around each t, we can minimize the effect of the t. Then, by carefully choosing the new tags, we can make the value of the Riemann sum turn out to be within epsilon of either 0 or 1, our choice. Our first step is to cut up the partition. There are n of the t, and we want their total effect to be less than epsilon. If we confine each of them to an interval of length less than, then the contribution of each t to the Riemann sum will be at least n at most. This makes the total sum at least 0 and at most epsilon. So let delta be a positive number less than. If it happens that two of the t are within delta of each other, choose delta smaller. If it happens that some t is within delta of some xj, and t is not equal to xj, choose delta smaller. Since there are only finitely many t and xj, we can always choose delta sufficiently small. Now we add two cuts to the partition for each t. One of the cuts will be at, and the other will be at. If one of these leaves the interval 0, 1, then we leave it out. T will be the tag corresponding to the subinterval. If t is directly on top of one of the xj, then we let t be the tag for both intervals. We still have to choose tags for the other subintervals. We will choose them in two different ways. The first way is to always choose a rational point, so that the Riemann sum is as large as possible. This will make the value of the Riemann sum at least 1 minus epsilon. The second way is to always choose an irrational point, so that the Riemann sum is as small as possible. This will make the value of the Riemann sum at most epsilon. Since we started from an arbitrary partition and ended up as close as we wanted to either 0 or 1, it is false to say that we are eventually trapped near some number s, so this function is not Riemann integrable. However, it is Lebesgue integrable. In the Lebesgue sense, its integral is 0, since the function is 0 almost everywhere. But this is a fact that is beyond the reach of the Riemann integral. There are even worse examples. IQ is equivalent to a Riemann integrable function. But there are non-Riemann integrable bounded functions which are not equivalent to any Riemann integrable function. For example, let C be the Smith-Volterra-Cantor set, and let IC be its indicator function. Because C is not Jordan measurable, IC is not Riemann integrable. Moreover, no function g equivalent to IC is Riemann integrable. G, like IC, must be 0 on a dense set, so as in the previous example. Any Riemann sum of G has a refinement which is within epsilon of 0 for any positive number epsilon. But if the Riemann integral of G exists, then it must equal the Lebesgue integral of IC, which is 1/2. Therefore, G is not Riemann integrable. Similar concepts. It is popular to define the Riemann integral as the Dabo integral. This is because the Dabo integral is technically simpler and because a function is Riemann integrable if and only if it is Dabo integrable. Some calculus books do not use general tagged partitions, but limit themselves to specific types of tagged partitions. If the type of partition is limited too much, some non-integrable functions may appear to be integrable. One popular restriction is the use of left-hand and right-hand Riemann sums. In a left-hand Riemann sum, for all I, and in a right-hand Riemann sum, for all I alone, this restriction does not impose a problem. We can refine any partition in a way that makes it a left-hand or right-hand sum by subdividing it at each t. In more formal language, the set of all left-hand Riemann sums and the set of all right-hand Riemann sums is cofinal in the set of all tagged partitions. Another popular restriction is the use of regular subdivisions of an interval. For example, the th regular subdivision of 0, 1 consists of the intervals again. Alone, this restriction does not impose a problem. But the reasoning required to see this fact is more difficult than in the case of left-hand and right-hand Riemann sums. However, combining these restrictions, so that one uses only left-hand or right-hand Riemann sums on regularly divided intervals, is dangerous. If a function is known in advance to be Riemann integrable, then this technique will give the correct value of the integral. But under these conditions, the indicator function IQ will appear to be integrable on 0, 1, with integral equal to 1. Every endpoint of every subinterval will be a rational number, so the function will always be evaluated at rational numbers, and hence it will appear to always equal 1. The problem with this definition becomes apparent when we try to split the integral into two pieces. The following equation ought to hold. If we use regular subdivisions and left-hand or right-hand Riemann sums, then the two terms on the left are equal to 0. Since every endpoint except 0 and 1 will be irrational, but as we have seen, the term on the right will equal 1. As defined above, the Riemann integral avoids this problem by refusing to integrate IQ. The Lebesgue integral is defined in such a way that all these integrals are 0. Properties. Linearity. The Riemann integral is a linear transformation, that is, if f and g are Riemann integrable on a, b, and alpha and beta are constants, then because the Riemann integral of a function is a number, this makes the Riemann integral a linear functional on the vector space of Riemann integrable functions. Integrability. A bounded function on a compact interval a, b, is Riemann integrable if and only if it is continuous almost everywhere. This is known as the Lebesgue integrability condition or Lebesgue criterion for Riemann integrability, or the Riemann-Lebesgue theorem. The criterion has nothing to do with the Lebesgue integral. It is due to Lebesgue and uses his measure 0, but makes use of neither Lebesgue's general measure or integral. The integrability condition can be proven in various ways, one of which is sketched below. In particular, any set that is at most countable has Lebesgue measure 0, and thus a bounded function with only finitely or countably many discontinuities is Riemann integrable. An indicator function of a bounded set is Riemann integrable if and only if the set is Jordan measurable. The Riemann integral can be interpreted measure-theoretically as the integral with respect to the Jordan measure. If a real-valued function is monotone on the interval a, b, it is Riemann integrable, since its set of discontinuities is at most countable, and therefore of Lebesgue measure 0. If a real-valued function on a, b, is Riemann integrable, it is Lebesgue integrable. That is, Riemann integrability is a stronger condition than Lebesgue integrability. If is a uniformly convergent sequence on a, b, with limit f, then Riemann integrability of all implies Riemann integrability of f, and however, the Lebesgue monotone convergence theorem does not hold. In Riemann integration, taking limits under the integral sign is far more difficult to logically justify than in Lebesgue integration. Generalizations. It is easy to extend the Riemann integral to functions with values in the Euclidean vector space Rn for any n. The integral is defined component-wise, in other words, if f equals then in particular, since the complex numbers are a real vector space. This allows the integration of complex-valued functions. The Riemann integral is only defined on bounded intervals, and it does not extend well to unbounded intervals. The simplest possible extension is to define such an integral as a limit, in other words, as an improper integral. This definition carries with it some subtleties, such as the fact that it is not always equivalent to compute the Cauchy principal value. For example, consider the function f, which is 0 at x equals 0, 1 for x greater than 0, and -1 for x less than 0. By symmetry, always, regardless of a. But there are many ways for the interval of integration to expand to fill the real line, and other ways can produce different results. In other words, the multivariate limit does not always exist. Computing yields a, and computing yields minus a. In general, this improper Riemann integral is undefined. Even standardizing a way for the interval to approach the real line does not work because it leads to disturbingly counterintuitive results. If we agree that the improper integral should always be, then the integral of the translation f is -2. So this definition is not invariant under shifts, a highly undesirable property. In fact, not only does this function not have an improper Riemann integral, its Lebesgue integral is also undefined. Unfortunately, the improper Riemann integral is not powerful enough. The most severe problem is that there are no widely applicable theorems for commuting improper Riemann integrals with limits of functions. In applications such as Fourier series, it is important to be able to approximate the integral of a function using integrals of approximations to the function. For proper Riemann integrals, a standard theorem states that if Fn is a sequence of functions that converge uniformly to f on a compact set a, b, then, on non-compact intervals such as the real line, this is false. For example, take Fn to be n-1 on 0 n and 0 elsewhere. For all n we have, the sequence converges uniformly to the zero function, and clearly the integral of the zero function is zero. Consequently, this demonstrates that for integrals on unbounded intervals, uniform convergence of the function is not strong enough to allow passing a limit through an integral sign. This makes the Riemann integral unworkable in applications, because there is no other general criterion for exchanging a limit in a Riemann integral, and without such a criterion it is difficult to approximate integrals by approximating their integrands. A better route is to abandon the Riemann integral for the Lebesgue integral. The definition of the Lebesgue integral is not obviously a generalization of the Riemann integral, but it is not hard to prove that every Riemann integrable function is Lebesgue integrable, and that the values of the two integrals agree whenever they are both defined. Moreover, a function f defined on a bounded interval is Riemann integrable if and only if it is bounded and the set of points where f is discontinuous has Lebesgue measure 0. An integral which is in fact a direct generalization of the Riemann integral is the Henstock-Kurzweil integral. Another way of generalizing the Riemann integral is to replace the factors xk plus 1 minus xk in the definition of a Riemann sum by something else, roughly speaking. This gives the interval of integration a different notion of length. This is the approach taken by the Riemann-Stieltjes integral. In multivariable calculus, the Riemann integrals for functions from Rn are multiple integrals.